Welcome back to Atomo Tutorials, and this is the last video, or one of the last videos, we will spend looking at substances or types of substances for topic 1 before we go into some calculations. But so far we've looked at 3 different classifications of elements and compounds, which have been ionic, simple molecular, and giant covalent structures. We're going to finish off by taking a look at metals, specifically the structure and bonding of metals and how this relates to their physical properties. So when we talk about metals, by the way, what we mean is the metal elements contained within the periodic table. All of the elements from group 1 on the far left of the table to this zigzag line separating them from non-metals. And the way metals actually arrange themselves is a lot closer to the arrangement of ionic lattices than it is to simple molecular substances. We can class metals as having a giant structure. If you had a slab of metal, whether it be iron, magnesium, copper, and you examined it closely, it would look more or less like this. You would have many metal atoms arranged regularly, more or less in rows like this, and they'd be tightly packed together. So the way in which metal atoms arrange themselves is quite similar to the way in which ions in ionic lattices arrange themselves, except the bonding that takes place in a metal structure is quite different. So if you remember back to when we were talking about graphite, what we said was that the carbon atoms in graphite had one electron which was delocalized, and because of this, graphite could conduct electricity because of the free electron, the delocalized electron supplied by each atom, and it could carry electrical charge. Well, in metal atoms, you have an outer shell which is incomplete and has a certain number of electrons. What happens is the electrons on this outer shell for each atom become delocalized. They essentially leave the outer electron shell and are free to move throughout the whole structure. And of course, we know that when an atom loses electrons, it forms an ion. So all the metal atoms lose these electrons and become positive ions. And from here, what happens is there is a strong electrostatic force of attraction between the delocalized electrons, which have left the atom, and the positive ions which have formed. This attraction is known as metallic bonding, and it is what maintains the metal's structure. So for something like sodium, we would have one outer electron becoming delocalized for each sodium atom, and the attraction would be between the sodium ions and the sea of delocalized electrons. For magnesium, we would have two free electrons, two delocalized electrons for each magnesium atom, and the attraction would be between these two electrons and the magnesium 2 plus ions. So the structure and bonding of metals is directly linked to their physical properties. And metals tend to have high melting and boiling points. This is because the electrostatic forces of attraction between the positive metal ions and the sea of delocalized electrons, in other words, metallic bonding, is very strong. And because the electrostatic attractions are so strong, a lot of energy is required to overcome and break this attraction. So most metals do have high melting and boiling points, and they're nearly always solids at room temperature. In terms of electrical conductivity, metals have free electrons, as we've seen. Free electrons within their structure, and these are charged particles capable of carrying electrical charge. Because of this, they conduct both heat and electricity, and conducts them very well compared to most non-metals. A couple of more properties that we haven't looked at before. We'll start with malleability. And malleability is basically the ability of a material to have its shape deformed and to be made into a new shape without the material breaking. And pure metals are quite malleable. This is down to their structure of having a regular arrangement of atoms. This arrangement, I've shown here, means that the rows, or the layers, can basically slide over each other if force is applied. So we can change the shape of a pure metal by doing that, by applying force. If we hit metal with a hammer or something like that, that would work, I would think. But finally, density, which is the last physical property we're going to look at. Density, in very simple terms, basically means the mass per volume of a particular material. So if we, for example, had two different materials of exactly the same volume, and material A was heavier than the material B, material A would have a higher density. And it turns out that metals generally have higher densities than non-metals, and there are very few exceptions to that. And this is simply down to their close packed structure. There aren't many gaps at all in a metal compound compared to a non-metal, which is usually a liquid or gas.